Hello, everyone. This is the problem video for section 8.1. So we got 8.1 problems. I feel like the material itself is fairly straightforward. So instead of doing problems from the book, I'm just going to skip straight to the homework because there's some just glancing at it that seem maybe a little weird. Okay. So first thing, first problem, number one, we have transformations of graphs. So it's a bit, I'm not sure yet why they included this. I haven't looked at the entire homework yet. I'm going to do that with you guys live. So I don't know why they included this right now, but maybe in a couple minutes I'll say, oh, okay, this is why they included it. So what they want us to do is they want to use, they want us to use transformations of the graph of y equals 1 over x. So like transform y equals 1 over x to graph something else, and you might have a different example, but what I have is s of x equals 2 over x plus 3. Okay, so what does this mean? Put my little square, that means I'm starting my problem. So remember, if we have like a graph in the xy plane, like 1 over x, let's look at 1 over x. What would that look like? Okay, that would look something like this, right? And then on this side, it would look like here. Okay. So this is the graph of 1 over x. And then if we kind of modify this equation a little bit, it has predictable effects on the graph. Okay, so in general, if I have like y equals f of x, let's think about this. What does y equal f of x plus 5 do? What does that do to my graph? Okay, this is going to shift our graph to the left by 5. Okay, so if I add 5 to x, that's shifting my graph to the left by 5. Okay, so let's apply that to this. Okay, and we can do these transformations in steps. Okay, so I'm starting with my graph of y equals 1 over x. I know what that looks like. It looks like this. It's one of these graphs that it'd be good to have a general idea of what it looks like in the back of your head. Okay, so now let's transform this to y equals 1 over x plus 3. Okay, so that's not exactly what this is, but it's like one step closer, right? So we'll deal with the plus 3 first, and then we'll deal with the 2 next. Okay, so what does adding 3 do? Okay, think of this as our f of x. Okay, so that's like our f of x. So what did I just, so right now, instead of f of x, we have f of x plus 3. So what did we say happens when we write this? It should shift our graph to the left by 3. So instead of having this graph up here, we're going to shift it to the left by 3. So this vertical asymptote in our top graph, which is just right on top of the y-axis, right? That's going to be shifted left by 3. So like 1, 2, 3. Okay, so our vertical asymptote's here, and then our graph is the same. It's just been shifted left by 3. Okay. So we've shifted our graph left by 3. All right, so we've taken care of the plus 3. What effect does the 2 have on top? Well, let's kind of go back to this general thing again. If I have y equals f of x, and I multiply that by, 5 or 2 or whatever, what does that do? It stretches it up by 2, a factor of 2. Meaning we take all our points and we multiply the y coordinates by 2. Okay. So I'll show you what I mean. Let's say we're looking at this graph here. at, okay, so what would this point be? Okay, this is our graph for y equals 1 over x plus 3, right? So let's see, at -2, we would have 1 over 1. So this point right here is -2 comma 1. Okay, so the x coordinate's -2 and the y coordinate's -1. Okay, and now let's say I wanted to transform this to get y equals 2 over x plus 3. I'm just going to multiply all my y coordinates by 2. Okay, so looking at this, my y coordinate goes from 1, and then it goes up to 2. I multiply by 2 to get 2, and the x coordinate stays the same. And I can do that for all my points, and it has this effect of just stretching my graph, multiplying all my y coordinates by 2. It just has this kind of effect of stretching my graph vertically. Okay. Okay. So I have something like this. So my final product would be, let's kind of put it in a new color, let's say blue. So this would be my final product. It's the same graph, it's just been shifted to the left and stretched by a factor. Okay, so really ugly, rough sketch. Hopefully it makes sense. Okay. So that's all for this problem. So just make similar transformations for your own problems. Okay. Number 2 is just a straightforward application of our arc length material from section 8.1. So remember, we'll do at least a couple of these arc length problems. So let's start with number 2. They give me y equals 4x minus 3. We want to find the arc length of this between -2 and +3. Okay, so what do? First, I find my f prime, like this is my f, right? So I need to find my f prime, so that'd be 4, just 4. Okay, and then my formula is square root of 1 plus f primes squared. So square root of 1 plus 4 squared dx. And then I integrate that from -2 to 3. So this is pretty easy because it's just constants, right? So this problem, there's not even much integration. This is ends up being square root of 17, right? When we simplify that, and that's just a constant, so we can bring that outside. And then I'm just integrating this. Okay, well, what is that? It should just be square root of 17 times 5. That should be my final answer. So really easy problem number 2. They do say you can verify this by using the distance formula. Okay, so since this is just a line, right? This is just our original equation, just a line, right? So what does that look like? Okay, it's got y-intercept -3. I got slope 4. So like, I'll do a rough sketch real quick. It looks like this. Okay, and we're measuring the length of this curve from what, -2 to 3. Okay, so let's say this is -2 and we go to 3. Okay, so really what we're doing is just finding the length of this line segment from this dot to this dot. Okay, since it's a straight line, we have this distance formula. All right, so remember what the distance formula is: y2 minus y1 squared plus x2 minus x1 squared. Okay, if we found out the x and y coordinates of these 2 points and then plug them into this formula, it would give us the same answer, square root of 17 times 5. Okay. Moving on. Number 3, similar concept, except instead of having a straight line, we have a sector of a circle. Okay, so we have something on the exterior of a circle. Okay, same concept. Okay, the integral might just be a little bit messier if I'm just eyeballing it right now. It should still be pretty manageable. Number 4, again, just an arc length problem. So number 5, I think, is a good one to review. There are some tricks in here involving perfect squares that you might not be able to spot immediately. Okay, so let's try number 5. That looks like one of these problems I'm talking about. So what I have is we have x equals y to the 4th over 8 plus 1 over 4y squared between 1 and 2. So the first thing we notice is that this is a function. We have x as a function of y instead of y as a function of x. We can do the exact same formula, except so this time we're going to be integrating in terms of y instead of in terms of x. Okay, nothing really changes. All right, so we're just using this equation and we're going to integrate in terms of y. This is not what the trick is. I'll show the trick comes in the integral. Okay, so let's see. Our first step would be finding our f prime, right? If this is our let's x, we could think of this as fy. So f prime y, let's differentiate this thing here with respect to y. Okay, so 4y cubed over 8 plus, let's see, this is 1/4 y to the negative 2. So the derivative will be negative 2 over 4y to the negative 3, right? So this is my derivative. And then let's go ahead and find f prime y squared. So let's go ahead and square this, right? We need to square the derivative. It's going to help to simplify. Let's go ahead and simplify this. This is 1/2 y cubed minus 1/2 y to the negative 3. Okay. And let's now square this. Okay. So follow along on your own. I'll kind of do some mental math here. That should be 1/4 y to the 6th. Hope I don't mess this up. Minus 1/4 plus 1/4 y to the negative 6. Okay. And now let's plug this into our formula and see what happens. Oh, and you know what? I've already spotted a mistake. This should be minus 1/2. Okay, so close call there, but follow along on your own. See if you get that same thing. Double check me. Okay. So now let's plug this into our integral formula, right? We would integrate from 1 to 2 along our bounds, and then we have 1 plus f prime squared. Okay, so 1 plus this thing. Okay. So this thing. Okay. Now to integrate in terms of y. Now check what happens. All right, so we're adding 1 to this. Okay, so really all that's going to change is I add 1 to negative 1/2, and then I should get positive 1/2, right? Okay, so once I simplify, okay, I get this integral. Now this is really similar to what we had up here, right? Look at this line up here. Okay, the only difference is here I have a plus, here I have a minus. Okay, and remember this thing here was what? It was this squared. Okay, so if I change this to a minus, does that have like a similar root as this, right? So this squared equals this. If I have a plus here instead of a minus, what do I have? Okay. Well, it turns out if we look at it a bit closely, this stuff here is actually perfect square, and it's equal to 1/2 y cubed plus 1/2 y to the negative 3 squared. Okay. So I have a square root of a square. So the square root and the square are going to cancel. Okay. And my integral just becomes this. And then once we're at this point, integrating this stuff's fairly easy, right? This is not a tricky integral at all. So I won't continue there, okay? So the trick is look for this perfect square on this problem, all right? And in other problems as well. This might pop up a couple of times on this homework. 6, looking at 6, I don't see anything that would be too crazy for number 6. So number 6, I have let's see, x equals 1/3 times square root of y times y minus 3. I don't anticipate anything being too crazy about this. Let me go. I would maybe suggest distributing this and see what happens. I won't solve the rest of that one. 7 looks a bit tricky, so we and let me know if this is trickier than I'm assuming it is, but it looks fairly straightforward for number 6. Number 7 looks a little tricky, so we have y equals ln secant x between 0 and pi over 4. Let's see. So I take the derivative, and I get 1 over secant x, and then I need to do the derivative, multiply by the derivative of secant. This is like chain rule, right? If I want to take the derivative of this. So it should be, let's see, secant x tangent x, and the secants cancel. And then the thing inside my integral should be 1 plus, okay, so my derivative is just tan. And if I square that inside my integral, I get 1 plus tan squared of x, and then there's an identity for this, right? This is equal to secant squared. Okay, so that's the only trick there, I think. Let's see, 8, is there anything? Cosh, oh, okay. So, yeah, cosh. This is the hyperbolic cosine. Okay, so cosine with an h on the end. I realize you probably haven't dealt with this much in your math careers, and we haven't done it at all in this class so far, I don't think. Just look up the identities. These are identities I don't even really have at the tip of my finger, so to speak. Like, I don't really remember these. Whenever I encounter them, I just look them up online. So this is going to be kind of similar to number 7 in that, like, okay, you're going to differentiate this. Just look up what the derivative of cosh, this is pronounced cosh. Look up what the derivative of this cosh is, and remember to do chain rule. So I believe it's I believe it's positive sinh, which would be hyperbolic sine. So I believe the derivative of this would be 1/4 sinh 4x times 4, right? Because we're going to multiply by this derivative. So we just end up with sinh of 4x. And then in our integral, we put 1 plus sinh of 4x squared. And then there's an identity. So look up the hyperbolic sine identities. And I think this is just equal to cosh squared. But again, look that up for yourselves. So you should probably end up with an integral of something like this. And then the square and square root should cancel. And you'll have something like cosh of 4x. And then you need to look up the integral for hyperbolic cosine. And again, I believe it's going to end up being like sinh 4x over 4 or something like that. Number 9 should be fairly straightforward. Find the length of, okay, so number 10. Let's look at number 10. Find the length of the arc of the curve from point P to Q. So this, it's just, they're throwing some, they're trying to muddy the waters a little bit. so I have, my problem is y equals 1/2 x squared. You're supposed to find the length of this curve between p, which is -1/1/2 to q 1, so 1/2. Okay, so really you just use the arc length integral formula on that function, and you just integrate from -1 to 1. Okay, the x coordinates here. All right, so I don't, they're just trying to confuse you guys with these p's and q's, so don't worry about that too much. Uh, find the arc length function, number 11. So I covered the arc length function a little bit. Remember, this is just going to be an integral, and it would be starting at, they give you a point P, and the x coordinate would be your starting point of your integral. And then your upper bound would just be your x, I'm assuming. And then let's see, so you should have like blah, 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 you have a function in here. I'll do this quickly. You have a function inside, and then you can integrate this. This should be something you can integrate to get a capital F. And then you'll be evaluating from x to 9. And then you could just plug these bounds in. So you would get something like f of 9, or excuse me, f of x minus f of 9. So that's kind of the general layout. Not too complicated. 12. It looks like just basic arc length integral, but maybe, we're integrating sine, let's see, derivative. Okay, so just look up what we're dealing with inverse trig stuff, so you'll need to be able to differentiate, take the derivative of something like sine inverse of x. Okay, and then you got to square it and then integrate it. So just, if you're having trouble here, just look up the derivative table for the trig stuff and see what the derivative of sine inverse of x is. And then the rest should be review. 13 looks like partial fractions review. 14 trigonometric review. 15 looks like probably a u substitution review. Let's see if we can do 15 real quick. So what I have is 3 x to the 13 e negative x to the 7. So what would that be? After looking at it for just a couple seconds, I would say this is probably a u sub combined with integration by parts. So let's see if you do u equals x to the 7. Okay. Then du would be 7x to the 6th. Okay. So let's plug this stuff into our integral. We would have 3 x to the 13 e to the negative u, and then du over 7x to the 6th. Okay, let's see what happens. We got x to the 13 divided by x to the 6th. So I should end up with 3 over 7 x to the 7 e to the negative u. But remember, x to the 7 is our u. So what I have is 3 over 7 u e to the negative u du. And then remember, we can do this. We could do this easily by integration by parts. So do that by integration by parts, and then remember to undo u sub at the end. Okay, so not too bad. Maybe you wouldn't spot that immediately. All right, so I think that covers everything, all the hard stuff on section 8.1. Good luck.